Let's take a step back and think a bit more generally about what exactly it is we want our voting methods to do for us. So remember, the question we've been wrestling with is which of the voting rules actually is the best. We've seen lots and lots of examples of different types of voting procedures, and we'd like to know which one of those voting procedures actually is the best. Now, let's think about that question for a moment. And you'll soon begin to realize that the answer really depends. It depends on why exactly it is the voters disagree. After all, if the voters all agreed, then there'd be no need to hold an election. There'd be no need for a voting method. But that's not the situation we're in. We're in a situation in which the voters actually disagree. So why do they disagree? Well, on the one hand, we might imagine that the differences in rankings arise because of erroneous judgments about the objectively correct rankings of the alternatives. So the idea here is that we have a set of voters, and they all generally agree about a common objective. And there's this set of alternatives, and we can think of these alternatives as different policies or different ways of achieving that common objective. Now, we're going to assume that there is some objectively correct ranking over all of the alternatives. What that means is there's some way we have, some objective way of determining which alternative is the best, and which alternative is the second best and third best, and so on, and also which alternative is the worst. Now, unfortunately, the voters are in a situation in which they don't know this objective correct ordering. They each have, let's say, different information, or perhaps even different ability to use the information and evidence they have in order to determine which of the alternatives is actually objectively the best. So in this case, what we want our voting rules to do for us is to somehow wade through all of these differences of information and difference of ability and latch on to the objectively correct ordering over the alternatives. So the question really is, which of the voting rules are more likely to yield the good outcomes, where the good outcome is this objectively correct ranking over all of the alternatives? But on the other hand, we might imagine that the differences in rankings arise because of differences in values. So in this case, it doesn't actually make sense to say that there is some objectively correct ranking over the alternatives, because the voters, their differences in rankings are not arising out of differences of information, but rather they may disagree about the common objective. Or even if they agree about a common objective, they may evaluate the alternatives differently. They may evaluate the alternatives on different scales. So the goal here is not to find some objectively correct ranking, because that doesn't even make sense. The goal here is rather to strike a compromise between the different rankings. So the question becomes, which of the voting rules selects the compromise, the best compromise between the different rankings? Now, in this lecture, I want to focus on this aspect of a disagreement. The idea is that the voters disagree not because they have different information, but because that they're ranking the alternatives or candidates, they're evaluating them differently. So our goal is to find a compromise between the different rankings. But what exactly is a compromise between rankings? Remember, rankings are just orderings over a set of alternatives. So they're these discrete objects. They're not numbers. Well, in order to find a compromise between the rankings, we first of all need a notion of how far apart one ranking is from another. That is, we need a notion of distance between two rankings. So the idea is that if we have two rankings, we have some ranking A over here, A over B over C, and another ranking over here, C over B over A. So these are exactly opposite of each other. We would like to know which of the rankings actually falls in between these two rankings. So in order to make sense of that, we need a way of measuring exactly how far apart one ranking is from another. Once we have a notion of distance, the next question is, how do you actually define a compromise ranking. What does compromise actually mean? Well, any statistician will tell you that you can either use the mean or the median. So to make these ideas precise, let's look at some old work by Kemeny. Let's start with defining what's become known as the Kemeny distance. So the key idea is that we want to understand in what sense is the ranking A above B above C actually closer to A above C above B than to B above C above A. So how can we understand this? Well, the idea is that if we start with A above B above C, in order to transform this ranking into the ranking A above C above B, all we have to do is we have to move C up one position. So we have to swap B and C. So we have to make one move to transform A above B above C into A above C above B. But in order to transform A above B above C into this other ranking, we have to make two swaps. We have to move A down to the bottom, and that's going to require swapping A with B and swapping A with C. So the distance there is 2. So Kemeny's idea is very simple. You look at these rankings, we look at all of the pairs of alternatives, and we ask on how many pairs of alternatives do they disagree. So note, A greater than B greater than C and A greater than C greater than B, they disagree on just the pair of alternatives B and C. This ranking ranks B above C, whereas the second ranking A above C above B ranks C above B. And those are the only pair of alternatives in which they disagree. So the Kemeny distance between those two rankings is going to be 1. However, the distance between A above B above C and B above C above A, they actually disagree on 2 pairs of alternatives. So they disagree on the relative ranking of A and B and the ranking of A and C. So the Kemeny distance there is actually 2. Now, here's a useful representation for the Kemeny distance between all rankings over 3 alternatives. So you may want to pause the video and double check my calculations here. And you can see what I have listed here. So there's a Kemeny distance of 1 between this ranking and this ranking. To figure out what the Kemeny distance is between A over B over C and C over A over B, well, we just follow the diagram. We find the shortest path between A over B over C and this node. And we see the shortest path is 2. So the distance between those 2 alternatives actually is 2. So this is just a useful way to visualize the Kemeny distance between all the rankings over 3 pairs of alternatives. Now we need to define the right notion of a compromise relation. We've fixed a notion of distance, the Kemeny distance between different orderings, and now we need some way of figuring out, using that notion of distance to define the compromise ordering. I mentioned already that we can borrow 2 notions from basic statistics, namely the mean or the median. Let me just remind you of the mean and median's definitions. So let's just for the moment suppose that we have a set of numbers, real numbers, natural numbers, whatever. And recall the following 2 characterizations of the mean and the median. Remember, the median is sort of the middle number, and the mean is the average of all of the numbers. But we have a different characterization of the mean and median in terms of distance. The mean, it turns out, is the number that minimizes the sum of the square of the distance between each data point and x. So the idea is we have all of these numbers, and we look at, for each number, a sub I, we look at the difference between a sub I and x. X is eventually going to be this mean. And we square that distance. So a sub I minus x is the distance between the number and the data point a sub I and x. And we square the difference. We look at the sum of all of these squares of the distances. And we find the number x that minimizes this sum. That turns out to be the mean. The median turns out to be, rather than squaring the differences, we just look at the absolute value of all of the differences. So we're just looking at the absolute distance between AI and X. We sum up over all of the data points, and again, the median is the number that minimizes that distance. Now, how do we apply these ideas to election scenarios? So imagine that we have the following election scenario. So 21 people prefer A over B over C, 5 people prefer B over C over A, and so on. So the first thing we need to do is we need to calculate both the Kemeny distance and the square of the Kemeny distance between each of the possible orderings, and then all the possible linear rankings of 3 alternatives. So just to read this table, when I write A next to B next to C, that means A is ranked above B, which is ranked above C. So we can fill in all of these Kemeny distances. So for example, if we look at this ordering right here, this is B ranked above C, ranked above A. We see that it has a Kemeny distance of 3 with its exact reverse. A ranked above C, ranked above B. It means it takes 3 swaps to transform this ordering into the ordering A above C above B. So the Kemeny distance is 3. The square of that Kemeny distance is going to be 9. Just to take one other example, let's take A ranked above B, ranked above C. We see that it has a Kemeny distance of 1 to the ranking B above A above C. And that's because it takes 1 swap to transform the ranking A above B above C into the ranking B above A above C. And of course, the square of 1 is just 1. So you may want to pause the video to double check my calculations, make sure that all these calculations are correct. However, remember that the data we actually had more than 1 person held this ranking. So in fact, 21 people held the ranking A above B above C. So we need to go through and we need to multiply all the numbers along the first row by 21. And we can then fill in the rest of the table. We have 21 people prefer A over B over C, 5 people have the second ranking, 4 have the third ranking, and 11 have the last ranking. When we sum up over the columns, we see that, for example, the sum of distances to the ranking A above B above C turns out to be 51. That's the smallest. This minimizes the overall sum. If we want to minimize the sum of the square of the distances, it turns out to be B ranked above A ranked above C. So these 2 orderings turn out to be our compromise orderings. A above B above C and B above A above C. So we see the median ranking is A above B above C because it minimizes the sum of the Kemeny distances, whereas the mean ranking B above A above C minimizes the sum of the square of the Kemeny distances. Both of these are perfectly good notions of a compromise ordering given this data. You might argue that the median makes a bit more sense in this context. For the part of the reason is 21 people rank A first, whereas only 5 people rank B first. Yet, according to the mean ranking, B turns out to be ranked first. So, for that reason, many people take the appropriate notion of a compromise ranking to be defined by the median ranking. So, the compromise giving an election scenario, the compromise ordering is going to be that ordering which minimizes the sum of the Kemeny distances.